Regression is the process of fitting a model to data, and we're going to be talking about this separately from classification. So for example, if we have a model that we want to generate from data, and let's say there's our data, maybe one of the simplest models we could come up with is just a linear model that fits this. And so our model is going to be something like y equals the slope m plus the times x plus b, where this is x and this is y, and these are the measured values right here, measured values, and we have predicted values. And one of the ways to come up with this model is to predict with this form, which is a linear model right here, and minimize the sum of squared errors between all of the points and that model. So we're going to adjust the m and the b, for example, in order to be able to fit this model. Now, you could do other types of models as well. You could have nonlinear models, you could have machine learned models, neural networks, and other types. It just means that this expression right here, the mathematical expression, is different, and we're still fitting or adjusting some of these parameters within our model to be able to make our prediction line up with the data, maybe with some kind of sum of squared errors or mean squared error or other type of measure. So we're going to go through a couple examples here. We'll start with linear regression, and then we're going to work on to some more complicated examples. And let's just first of all generate some data. Okay, so here is our data, and to apply linear regression, we can do that a couple different ways. We can use the NumPy polyfit. All right, and if I run this, I'm going to get a slope and an intercept. All right, the intercept is going to come right down here about negative 1.31, and the slope, you can see it climbing here at a slope of 4. All right, now we can also calculate things like R-squared values. You can import scikit-learn metrics. You import the R2 score, and all that you have to do there is plug in your measured values and your model values. It doesn't matter which order. You can put these as model and then measured, and then you could calculate your R-squared. Now that isn't necessarily the best measure, but it's a very common one to be able to tell how well your model is fitting the data. All right, one of the things you need to watch out for with linear models, especially when you have a lot of the standard packages assume that you by default are going to go through an origin of 0, and so you need to add on a row or a column of 1s, or you can add a constant to your model. So that's going to give you an intercept. So if I run this, this is stats models API, and this shows some more information about your least squares, ordinary least squares, regression results for this model. Here's your intercept, and there is your slope. So you can see it gave the same answers for the intercept and the slope, but a little bit more information about the statistical significance of each of those and some of the other types of measures that show you if the error is normally distributed, and of course the R-squared value right there with adjusted R-squared. Okay, so some very interesting information. This is very nice for generating some of the standard output from linear regression. All right, let's go on to a linear regression activity. So go ahead and copy this. We want to calculate the slope and the intercept and be able to also calculate R-squared values. So let's go ahead and just do the easiest one, which is NP polyfit. And then that is going to be XR, YR, and we'll just do a linear model, and then we'll print P. Okay, so there's my slope and my intercept. I could also use the stats models one as well. All right, and then we want to calculate the R-squared value, R2 score Let's go ahead and just grab that. We haven't imported it yet, but there is the, okay, there is how we use it. I'm just going to copy this down here. Okay, so r squared, we have measured and model. Our measured, of course, is going to be yr, and then we also need to do np, and then this is going to be polyval. We're going to evaluate our fit with p, and then comma, and then we'll put in xr to give us our predicted value right here. And let's just go ahead and run that again, and there is our r squared value. Okay, let's go on to the next one. Oh, we forgot to show the data and the linear fit on a plot. All right, here we go, plot, and we'll do xr, yr, and I'll do some red dots, and then let's get xr, and then put in this polyval, and we'll make that a black line. Okay, so there we have our fit. Okay, let's go on to the next one, polynomial regression. Very similar to what we learned with, polyfit. We can, if we put a 1 here, that's going to be linear. This is going to be a quadratic with a 2 here. And if we just run this, you're going to see the polynomial coefficients and then the predicted regressed model here that fits that. That's just a quadratic model. Okay, there's more information on the regressed coefficients if you use the stats models. Okay, a polynomial is just really a linear regression, but you include x squared, x, and then some 1s there, and then you can see that you have the different coefficients, okay, of x squared, which is this x1, x, which is x2, and then you also have your 1s, which give you your intercept. Okay, so there are the, it tells you the statistical significance of each of those, if you should have those. For example, if you go up to, a higher order, let's go up to 3rd or 4th or 5th, and even 6th. Okay, you run it again, and then you can see the statistical significance, how many you need to get a good model, and so at a certain point you're going to have more polynomial coefficients than you have data sets, so it really becomes meaningless because you have a perfect fit between those, and you're just adding additional complication to your model. Okay, let's do a polynomial regression activity. We want to take this, and same thing as before. I'm going to have my polynomial coefficients. Probably the easiest one is polyfit with xr and yr, and then it doesn't say what order. I'll just do a 3rd order polynomial, and then I'll show the polynomial on a plot. xr and yr, red dots, and then let's also plot xr and np polyval with p and xr. Okay, so there we have some of the values. Now, one of the things is this looks like a linear regression, but it's not. And so one of the things we might do is just say, create some new points in between. I'm going to go between 0 and 5 with 100 points. And then instead of xr, I'm just going to put in x. Okay, and that's going to smooth it out because I'm calculating this at more points than just at the data points that were there. Okay, and so if I put this down to a 2nd order, you can see it doesn't fit quite as well. 3rd order does a very good job of fitting all of those points. All right, now nonlinear regression, you've got to use a different tool. And sometimes these don't converge. And so there's some things that you need to do to help it find a solution. And we're going to use the SciPy optimize curve fit. Now you can see here okay, I have operands cannot be broadcast together with these shapes. Okay, so the very first thing I need to do is figure out what I did with the data. I think I redefined x, and I shouldn't have done that because I did that right here. Let me go back up, and I'm just going to regenerate my x data that I need for this example as well. So let's go up here and get it right here and just regenerate this because I overwrote the x value. All right, and coming back down here to the nonlinear regression, I'll run this again, and there I can see that it fit. I had a nonlinear model, which is a times e to the b times x, and a and b are my unknown coefficients right here, and it returns from this function, this new function. It uses that in curve fit. There's f, and then I put in my two measured values, my x and my z, and then my unknown coefficients are my next arguments in my function. So I could add a third one if I wanted to, and then it would be something like this. It might fit just a little bit better with that third coefficient right there. Okay, you probably haven't seen the asterisk here. What that basically does is it, with your parameters, those are these three parameters like that, it puts them in as if you are doing A, B, C. If you had split those out here, like so, and then put those in individually, you can do that and you should get the same answer, or you can do the asterisk and it's going to place those in there for you as if you had split them out like this. So that's one of the nice ways to not have to unpack them and then put them into your function. You can just use the asterisk p. All right, so let's do a nonlinear regression activity. Here's our nonlinear function, and we have some data. All right, and let's just use create our function. We're going to define a function, and this needs to be in the form that that SciPy optimize is going to need. Okay, so I'm going to say f of x, a, and b, and then I'll return what that prediction is. So that's going to be a times and then np log and then b times x. Okay, log is the natural log. If you do log 10, that's log based 10. All right, and then we want to do p and then p covariance. That's your covariance matrix. Okay, curve fit and f, and I'll do xr, yr, and then I can put in additional options there. I won't do that yet, but if it doesn't converge, you can put some of those in. Okay, and then let's just plot this xr, yr, and do that with red circles, and then also the let's go ahead and do our evaluation of this with our new fit function. And I'll make that a blue line. Now it doesn't have all the values in between, but we'll just try it. Okay, so it says we can't multiply the sequence by a non-integer type. All right, so what's going on here? I think what I probably need to do is convert these to NumPy arrays. Okay, I normally get that error when it's something about integer sequence or something like that. Okay, so just convert it to a NumPy array and then everything will work. All right, so you can see the fit. It does a pretty good job. I could add some more points in there and be able to smooth that out, but then I would probably end up redefining my x variable again. All right, so let's see. So this one, if you needed some extra things, like let's say it runs out of iterations, or let's say this is a 0 value right here, you're going to get an error, and that's because it evaluated that as log 0, and that was not a number. So you might get some things like that that You don't know why it's converging. If you run out of iterations, you can add in extra like max function evaluations, and you could set that to a higher value than the default. You could also put in initial parameter values. So if you want to change the initial guess, you can do that here with p0 and then put in some initial values for a and b. Okay, all right, that's it for this one. Let's go on down to some more machine learning topics. So these are computer algorithms and statistical models that rely on patterns and inference. They perform a specific task without explicit instructions. So that's kind of the definition of machine learning. You can have something as simple as linear regression or as complex as deep learning. With a neural network model with multiple layers. So this is going to demonstrate some of those with scikit-learn, which is a nice package. It started out as a Google Summer of Code project and then has kind of developed into a standard way to fit and predict from some of these models. And you can also make some of these notebooks interactive with Matplotlib notebook instead of inline here. I'm just going to use inline because it's a little bit faster. All right, so here is my data set right here. And let's go ahead and just first of all scale the data as we've learned and split it as well. Okay, so if you want to scale it, you could. You just use that. I don't think we need to scale this. I mean, it's looks like it's pretty well scaled already. Okay, so I'm just going to not scale it just for the purposes of plotting. Now here's a function for plotting. This isn't really going to produce anything, but you need to run this just so you have the fit function available. And what this is doing is it's creating some points on a mesh grid, and then it's going to fit, okay, with the training, which is your x and y, and then training, which is z, and then you're going to predict from the regression, and then it just reshapes it into sizes that you need for the plotting, and we're going to compute an r-squared value and then add a plot that shows the fit and the data. Okay, so just run that. We're going to run through linear regression first. So here is just a 2D, well, a 3D plot, but a 2D model, 2 inputs and 1 output that shows the linear plane of how it fits this model with a least squares. Okay, and let's do another algorithm, which is k-nearest neighbors. Now, you're looking at something that's going to fit a little bit better. Now, this does not use something like a linear model. It's just looking at the ones around it and trying to predict what the point should be just by looking at its nearest values around that. Okay, k-nearest neighbors. There's also a classifier that's very popular. This one's a regressor, so it's trying to predict continuous values. Now here's a support vector regressor, just like a support vector classifier. Okay, and this one has a very good r-squared value. You can see this one's a little bit smoother than this somewhat discontinuous or a little bit rough prediction with k-nearest neighbors. Okay, I'm going to keep going down. Multi-layer perceptron. This is a neural network model just with 3 neurons in 1 layer. Okay, and I could add additional layers here as well if I wanted to try to get a little bit better fit for the data of the data. So this would be classified as deep learning because I have multiple hidden layers here, not just a single layer. Okay, you can change the activation function, for example, to the ReLU function or sigma or others. Seems like for this this one, a hyperbolic tangent function works pretty well. Okay, let's go on to the regressor activity now. So there are many different options out there for regression, and here's some of the documentation on those for regression or classification. what I want you to do is just try another one. Okay, so go out and learn about another type of regressor and apply it. So in this case, I'm going to use the decision tree regressor. I'm a little bit scared of a passive-aggressive regressor. All right, well, not actually, but here we go. I'm going to go ahead and just run this, and you can see that it had a 0.98 r-squared value. Now you might try some other criteria here, the options, and you can look those up in the documentation. I'm going to try criterion for how it fits, and I'm going to use the Friedman MSE instead. And so let's just see Friedman, no, it's not dash MSE, it's underscore MSE. Okay, so improved it maybe just slightly. I can also do the mean squared error and others. Okay, so you'll have options associated with these, and that's where a lot of the tuning takes place, is these options for these different regressors. All right, let's go on to deep learning. Here is an activity with a Gecko package, and this one has uses the Gecko brain, which is a module for deep learning, and it adds different layers. So not just all the same, but it has a linear layer, hyperbolic, linear, and output linear. And then when you train it, you're going to see a fit to the data. There's just a sine wave right here with these. Okay, so that's another option for constructing something like a neural network regressor of the data. All right, let's go on to the TC lab activity. This one, we are going to do some regression, but first of all, we need to collect the data. So let's just import a few packages that we're going to need. I'll need the TC lab, and then I'll also import NumPy. And let's just say that the number of data points we want is 61. And I'll just do linspace. We're going to do that linearly spaced values with our n values. That gives us a time point every 0.5 seconds. And then we're going to make some space for the temperatures. And I'll just do empty like t, and do that same thing for T2 as well. All right, and then let's go ahead and connect to the TC lab as lab, and then set our heater value to 80% for one, and our heater value to 60% for number two. And then I need a loop here for I in range n, and I want to collect this many data points. So the very first thing I want to fill in is T1, and that's going to be lab.T1, and then I'll also do T2, and that's going to be equal to lab.T2. So every cycle I'm going to collect those, and then we can also print them as well, T1i and T2i, if you'd like to see those as it's going. Now let's go ahead and just sleep, and we'll sleep for 0.5 seconds. So this is what we need to do to collect the data, and then we're going to run some regression activities. This one's going to be going just for 30 seconds, so half a second each, and you'll hopefully be able to see it start to heat up a little bit in that 30 seconds. So you can see the temperature on both of them. This one, this heater set to 80%, and so you can see it rising just a little bit more than the other one. The other one also has a heater power factor set to half of that of the first one. So even though it's set to 60%, it's just not going to rise as high. All right, let's do a linear regression as the very first thing. The very easiest way to do that might be the polyfit. And I'm just going to, with this one, do polyfit and this one is going to be our time value. Let's just make sure we have that right. Okay, T1 and T2. So let's just create T and T1. Oh, this is supposed to be for T2. Okay, and we are going to do a linear model, so I'll put a 1 there. Or you can do kind equals linear. All right, and if I just run that, here is my linear model, and I could plug in the slope and the intercept myself. Okay, there's the slope and there's the intercept, or I can use Polyval to do that for me. Okay, so let's add our plot, and T and T2, and I'm going to make this as blue circles. All right, and then I'm going to plot T, and then also our linear regression, which is going to be NP Polyval, and I'm going to plug in T there. And let's make this one a black line. Okay, let's see. Oh, I forgot the P value there. All right, so here is my regression that you could see, linear regression of the data. Okay, so let's go on down to the nonlinear regression. We want to create a nonlinear regression for T1. All right, and this one is going to be using the curve fit, but we're also going to use a scikit-learn. We can use Keras or TensorFlow or Gecko for doing this. So let's go ahead and start. I'm going to define a new function. I'll just do f with t and then a, b, and c. Those are the ones that I need. And I'll just return the evaluation of that function. So a times b times numpy exp of c times t. All right, so there's the very first thing I need, and then I need p and p covariance and curve fit, and that'll be f, and then t and t1. Okay, so there I have my nonlinear regression. I've just fit this to minimize the sum of squared errors, and let's go on to the next one, which is to calculate the r squared. Okay, so r2 score, I think this is already imported, and I'm going to have T1, and then I also have my function with T and then P. All right, so there is my r squared value for my nonlinear function. Let's just go ahead and plot this just so we can see it. That's going to be T and T1, and I'll do let's just do red, and let me get my function here. Okay, and this one is going to be a black. I'll do a blue line, blue dashed line. All right, so there is my nonlinear function fit. It did an okay job, probably a better form that you could think of that would fit it better. Okay, but let's use a different model now. Let's use a neural network as well, a multi-layer perceptron regressor. And I'll have some hidden layers on this, hidden layer size, and I'll just put 3 for now. And let's see, the other thing we need is activation function. Let's do a hyperbolic tangent. That seemed to work well before. And a solver, we'll say limited memory BFGS. Okay, so that helps us get the approach. All right, and the other thing that we need is to just reshape this. It doesn't like a row-oriented input, so I just have to reorient it into a column-oriented, and then I'll say that my fit it. Okay, and this is going to be my model TR and T1. All right, and then my predicted values, those will come from my predict function. And let's get my r squared value as well. So just like I did before, I'm going to have t1, and then, well, actually there's a scoring function here, which is nice, which gives that to you automatically. So you can do nn score, and that is going to be tr and t1. All right, so that's good to print out our squared value, and then let's add this to the plot as well, our neural network. And we are going to do t and tp, which is our prediction, and we'll add those as black x's. All right, and let's see where our first, okay, so hidden layer size, hidden layer sizes is the correct one. All right, so there is our neural network model. We didn't have to necessarily come up with the correlation like we did here. We had to come up with a function form. We just used 3 hyperbolic tangent functions essentially, and then let it figure out how to fit it. Okay, so here's 355. This one's maybe even just a little bit better, just some more layers on our neural network. Okay, so that includes this tutorial on regression. I realize we went really fast through this. You're probably feeling like, wow, that was a lot of different options. I would encourage you to go back over this, maybe learn about some of these different types of regressors and their strengths and their weaknesses. There's also, we're going to get into classification, and if you go to the dynamic optimization course, you're going to see some additional information on regression and classification. And so if you feel like you need just a little bit more information on things like deep learning or classification, you can come here and work through some of the examples.